Okay.
And tomorrow you have no problem. Are we going to that thing or not? We're going to go. It's like I told everyone. They're asking me.
I don't know what to expect.
It's fine. Yeah.
So, welcome again, Ladina, and she'll give us the second half of the black hole. So we ended with, it's an object that only has 3 characteristics that we care about. Now we'll continue on with the first kind of processes. So the idea is, or kind of what our overall goal is, we want to find these processes that Renata talked about in the first lecture. First class, and then at the end calculate the internal energy. And for this, we need to find exactly these processes. So for this, we are considering so-called Penrose processes. And we can do those. This is actually why we looked before also at rotating black holes. So at the moment, we just look at, to make it a bit simpler, we look at black holes where the charge is 0. So we only have to keep ourselves busy with the angular momentum. And now I'll draw, you remember maybe in the last lecture, I drew this picture of the ergosphere, but this time, for that time I drew kind of a side view. And now I'm gonna draw a top view. So the rotation axis would be out of the board. So we have kind of the event horizon, and then around it we have the ergosphere. So we're now looking at it from the top. And in one of these Penrose processes, we have an incoming particle which comes in from infinity with energy E0 and angular momentum E0, L0, which then in the ergosphere splits into 2. So there is kind of a decay or a splitting, and 1/2 of the particle falls into the black hole, while the other half escapes away to infinity. So these then have energies E0, L1, and I'll change the indices so it's consistent with the lecture notes and I'll not get confused. L1. And then the black hole, or its mass and angular momentum. So we just look at now the initial states and final states of this process. So we have this Penrose process, that's P, which I label by kind of what the incoming or the infalling particle has for angular momentum and energy. Just some initial state, and the final state as these constants are conserved, M1. So we can change with these processes the mass and the angular momentum, but now maybe also in preparation for calculating the energy, I can actually do these processes in a reversible manner. And now maybe reversible is a bit confusing because we throw something through the event horizon and we'll never get it back. But with the reversible, we actually see that there exists exactly this reverse process, which will also be a Penrose process, where we change the state back again and we do exactly the negative work. So that's what I forgot to add. The work of this process on the black hole is just 0 minus 2. Also, as I said, this energy that we can define is conserved under particle decay, or so we have this relation between it. So now we kind of split our entire process, which we want to make a reversible process, into many small processes. So we make our energy of the incoming particle very, very small, and then in the end take the limit to very take the limit. And we want to make it such that we can actually reverse this infinitesimal process. And it is the case that this process is reversible if you do this decay at the event horizon, and you do this decay such that the particle that falls in actually has infinitesimally small radial speed. So the speed would then intuitively get lost because, or the energy would get lost because, you can only, because what you do in these kind of processes is that you extract the angular momentum. So maybe I can, to make this a bit more clear, I'll write down kind of the relation. So you can then derive a relation between what the energy of this part of the infalling particle and the angular momentum of the infalling particle has to be, such that you are in its reversible. Here we consider it differentials, or very small, so I just write differentials. So we have our plus is again in the event horizon. Where these are the quantities or the state of the hole. So you see that if to reduce the energy of the black hole, I have to have counter-rotating, or have to have an angular momentum of the particle which is exactly opposite the angular momentum of the black hole. So I have in the end lower angular momentum and lower mass. So I take out mass, and if they are in the same, so they have the same sign, then the energy will increase. So I can increase and I can decrease. And I can always, so I can then do many of these processes. And if I do this, so I will find that I can reach all states which are in this relation with each other. So for all states, it will hold that the irreversible mass, which is,
Can you write a bit larger?
I'll write it again on another board. So for all states, I can reach via these reversible Penrose process, is where it holds that the irreducible mass is constant. So for both the final and the initial state will fulfill this equation. So maybe it's useful to show these kind of which states you can reach in state space, which is then just states which we have here mass, and here the angular momentum, and then we have this restriction, which this gives me two parabolas that I can't reach. And in the end, this equation gives me, I can reach states which lie on first, and so on. So I can change. So I change the again. I extract angular momentum, so the angular momentum decreases and the mass also decreases. And for any mass, so that's also why it's called the irreducible mass. If L is 0, this is really the irreducible. Just the lowest mass I can arrive to during one of these reversible Penrose processes. While now I can only reach states on these curves. This is already good, but I need one more. I need to move also between these curves to be able to have the first law. So what I can also do is I can just throw in particles with no angular momentum into the black hole. And what I would do is then I would just move irreversibly then in this direction. So now we have these two processes, and we can also the concept of Penrose process can also be generalized to charged black holes. So one can also look at these, and then you will not get curves, or then your state space will be three-dimensional, and you will get surfaces on which you can move reversibly, and again, the lowest mass you can arrive to is the irreducible mass. So now we have found processes. We fulfill the first part of the second law because we have found all these processes. The second part we also fulfill because the work we do is really always just the mass, or directly related to in all of these processes is directly just the mass change, which also just gives you the hint to what the internal energy is, because the work we do is always given by the mass change in both of these kind of processes. So energy is then just given of a state ml, and then just given by the work of these processes, and the sum over these processes plus some constants to the reference state, because we saw we can always go from one state to the other via Penrose processes or just throwing in mass. So maybe I clarify how to do this very. So see this. If you are on one of these, or you're always on one of these Penrose processes, so you just go down and remove all of the angular momentum, then throw in so much mass that you're at the irreducible mass of the target state, and then go. And because you only need to go one way, you can assume that your initial state always has a lower irreducible mass than your final state. So this is then just the change in mass during these processes from your so maybe m minus m0 plus m0, and then we found that the internal energy we find in this framework is just the mass plus the constant. We choose our constant cleverly, or this to be m0, we can just make it the mass. But this is just nice choice of mass. So now our next goal is to compute the entropy. And to do this, or maybe I quickly repeat how the entropy is calculated. So you have the entropy of any system is then given by the entropy of your reference state plus the sum over the heat during the processes Pi and temperature, where each process Pi is the process which acts on your system and the reservoir. So what you do, and it's reversible. And there's also a postulate which Renata didn't mention, but to make sure that for all states this exists, we also need to make sure that this exists. So the PIs also need to concatenate in the right way. So P1 and the initial state of that is just your sigma 0, and the final state is your 6. So you find reversible processes from any state to any state, but what you're kind of given more than the first law is that you're allowed to couple to a reservoir. So we need to find this. We've already found one reversible process, but as you see in this graphic here, you can you cannot get from, you can only move on these curves, or if you consider charged black holes on these surfaces, but you cannot go from any state to any state. But what will tell you, what is maybe initially, or just as an intuition, what tells you is that these states, because you don't couple to a reservoir, you already know that these will have the same entropy. Reversible work processes. So let's keep this in mind and try to find these processes. So if you just look at the classical PR, there's actually a theorem called Hawking's Area Theorem. Which says that for all kind of classical processes, the classical, I mean, it's not we don't consider quantum mechanics, the area, which is very much related to the irreducible mass, can only increase. So now is the question, are we in trouble? Can we not find these processes? And the question, the answer is not really, or we can answer this because this theorem only holds for classical processes, and as soon as the black hole can evaporate, obviously the mass can differ. This theorem no longer holds. So we have to be able to calculate the entropy in this framework, we need to consider evaporating black holes. Another reason to see this is if you just consider classical black holes, coupling it to a reservoir wouldn't make much sense. So if you consider putting a black hole in a container full of gas and you wait, at some point every particle will fall into the black hole and your container of gas will stop. So coupling it to a reservoir will make sense. So we consider black holes. Now, one concern one might have, one implication from the first law is that you can always find a process which is the identity process. Because the first law says from any state to any state you can find a process. So in particular, you can find a process from one state to itself. So this is then called the identity process. And if you radiate and you just leave your black hole alone, it will at some point be gone. So now let's see that our processes are kind of fast enough that our black hole will not shrink too much while we leave it alone. But this is also not a black hole specific thing. If you leave a gas in vacuum, it will also cool down. So and radiate energy. So you don't have to. This is not very black hole specific. So now let's consider this reversible process. But let me first board. Other board.
There are questions about the first part. This could be a good point.
I didn't understand why it's reversible as a process.
So the idea, or very intuitively, it's you just you make your particle or first you can make the energy negative, or so you can always make the energy, or intuitively you can always throw in stuff into the black hole. Or
How so?
maybe I draw it again. So you have your ergosphere. Then you do this decay at the event horizon. And then one will go in. Now I don't have space to draw it anymore. And so it's two, sorry. You can make the energy of the infalling particle here, so both negative and positive, and you can always find both processes. You can find a process where it's positive and where it's negative.
So you're saying that you can make the decay in such a way that you're extracting energy from the black hole?
Yeah, you can extract it again, and you can also put it in again. And you can do this in such a way that it's exactly the opposite.
Mm-hmm.
And then to get the reversible, so this is really, you put in only a little bit of energy into the black hole, and then you do it again and again and again, so you can reverse it back. So you put in like also you can go very slowly and not to get it reversible. So now we need to find this kind of second time reversible process. And what we do for this is, again, exploit the fact that our black hole can rotate. So we put our black hole in a rotating reservoir, which rotates at the same speed as the black hole. Is given by you also say that the temperature of this reservoir is the same as the Hawking. So we kind of assume for this process to be reversible, that the temperature of this reservoir has to be the Hawking temperature of the black hole. And then we again do kind of this separating in very small processes.
So what's the Hawking's temperature? Did you introduce it already?
No, I didn't.
So write it down just to give an intuition.
Yeah. So Hawking's temperature for non-rotating black hole is just 8 pi over m mass. Where? No. Over the mass of the black hole. And this is just the temperature of the radiation that the black hole radiates. And the reason we want them to be the same is that the radiation of the black hole just is the same as the or the that's how we imagine this. So we split these processes into 2 steps. So in a first step, we do a Penrose process. Where we change again the mass by just some dm, which if you plug in the omega we saw before in the formula for the work, is just actually given by the speed of the angular speed of the black hole times the change in angular momentum. And then in a second process, we increase the speed of the reservoir. to match that of the black hole. So we now do the same amount of work as before, but because we always are in thermally connected to a reservoir, our paths in for the states will be such that the Hawking temperature is constant. So you then change the angular momentum. So this would just be of a non-rotating black hole, but if you then rotate it, you can actually find temperature. So maybe an analogy to this process with an ideal gas is if you see the Penrose processing as adiabatically expanding an ideal gas, this would be kind of adiabatically expanding a little bit and then thermalizing it with a reservoir, adiabatically expanding a little bit. So, and if you do this in small enough steps, the process is reversible. Yeah. So with this, we have enough processes to reach all two states. So maybe I can again draw this diagram. Like the overview. So we have again these forbidden areas. We have the Penrose processes. And then we have these lines of constant temperatures. So around like this. And with this, we can now always first, or for simplicity, we can always take a state, move it to its irreducible mass, then take the state with the temperature, move back, so forward, and then get to the right angular method now.
Can you match these new lines you drew to the process you just described?
Yes, this is Penrose, and maybe I draw these in red. And this is the process with so with these two processes, we can calculate. So let's do this. So in case now that we have very many small processes, replace this sum by an integral, and the temperature always stays the same. So either we have no heat in the Penrose process, we don't exchange any heat with any reservoir. So this is the zero, so the temperature, we also need, or temperature can be anything. And in the Hawking process, the temperature, or in the process with the reservoir, the temperature is always the same. So let's now try to calculate this. Maybe leave this side open so we see what we are doing. So first, we need to try to find the integration funds. And it's easier if we just consider one case that M1 or the mass of the initial black hole is smaller. Well, not maybe let's start with. So first, we can always assume that our initial and final states are form 2 and 2, because we can actually just move on these Penrose processes without contributing this integral. So we can, for simplicity, assume that these states, additional final states. Second, we also say that M1 is smaller than M2. We can also do the opposite. Then we just have to consider the process we now derive in reverse. And this is a reverse process. The sign here will just be different. So we'll just get the different entropy difference. So we can do the same thing, but for simplicity, we only consider one case. So now, as I said, we start out somewhere here, then we move up on the Penrose process to reach the temperature of our second state, then move over to get back to zero, to zero. So we have this intermediate state. That's really important for this integral, because the Penrose process contributes. Which is this M. And for this, it has to hold. So it has to have the same irreducible mass as my initial state and the same temperature as the final state. So the first is just that the irreducible mass is given by, it has to fulfill this, and has to have the same temperature as the final state. I write down the Hawking temperature for a rotating black hole. Okay, so then we can calculate actually these mass of the state. So what we do is we plug in this equation into this equation, and we plug in the results for L to get from this equation.
Tell me what you're pointing at.
Maybe so. We use this equation, we solve it for L, or L squared, and plug the result from this equation into so we find that then L squared is just 4 M1 squared M squared minus 1 squared. We plug this into this equation and solve for M1. The reason I solve for M1 is because we'll find this expression then later, and it's nice to already, or it will be useful once we calculated the integral to simplify the result. Sorry. equation, so it's like this. So this is the expression for M1 given in M and M2. And we can also find an expression for M. And then with the above equation, we can also find an expression for L for the intermediate state. So now that we have found at least the bounds of the integral, it's worth to also take a look at the integrand. So the flowing into the reservoir is just given by the change in internal energy minus the work, which is, as we saw, this change in mass minus omega L. But because we now, it's easier to have both integrands on mass, so we can use kind of how L and M are related during on the path to write this as something Vm. And if you actually do this, you find that this is Vm minus so now we have everything. Yeah, M to M2. So now that we have all kind of the ingredients, we don't have to perform integration. So from M to, or what I wrote before, M calculate here over T. That makes the expression already easier because omega and T have the same denominator, so they can stop it. So now that we have this, we can just perform integration, and after some calculations, you find that this is just given by M minus M2. It's a bit more complicated, but also hard. So you find So if we then do some simplification of everything, find that this is just 4 pi the mass squared, or the irreducible mass squared if you actually consider all states and not just the reduction of the, we already simplified to always going to the irreducible mass via the Penrose process. And you can also relate this back to the area theorem. This, if you remember the formula for the area, it's also the area. So the area theorem really said that the entropy is always increasing. And we then actually also.
Can you just clarify if you use the theorem or if you demonstrated it?
Interpretation, but if you look at the theorem through the lens of this entropy, you see this theorem really said, okay, the entropy can only increase. Then, because we just started out with, so now I actually only consider rotating black holes, but because you can also generalize the Penrose process to charged black holes, our assumption here that the initial state and the final states are non-rotating can also be generalized to charged black holes. So we've really found the entropy for everything. Or for all states in Europe.
Yeah, so then before going for a break, can you just summarize?
Yes. Yeah. So what we did is we looked at we looked for processes to be able to fulfill, to be able to calculate the internal energy and the angular momentum. We found these processes, and then with these we could calculate the internal energy and the entropy.
And in the next lecture,
we will look at temperature and the get-off process. So the process, Renata already described in the first lecture as an example process. We look at the process.
Okay, so then we can go for a break. Thank you, Ladina. 10 minutes. No, 15 minutes. We said at 12+. All right, so again, just to summarize, what we did so far was just like to build a Carnot cycle or a Roto cycle, and I have one and exactly we need to find different types of processes, like it's adiabatic, isothermal, and combine them to get the cycle. Then Ladina found these two processes, the Penrose and this new one, goes around, that allows us to reach any state reversibly. And from here, we computed the entropy of the black hole, which reproduces some null results that were, achieved in more complicated ways than this. And now we go to the temperature.
Yes. So Renato didn't talk about how you can find the temperature of a system. He talked about how you can find the temperature. But the temperatures of systems can also be defined in this, or for some systems can also be defined in this framework, but you need to introduce a bit more. So you need to actually look at this. Then we looked at they're then called quasi-static processes, where we really consider each process to be splittable in very small processes. And there you can define the temperature of an object just as, or in general, as the internal energy derived to the angular entropy. So we also apply this result to black holes, and if we do this, we do find back again exactly the Hawking temperature found before. So now I write it also down for charged black holes. So we find the Hawking temperature now also for charged black holes back, and this is has to, or it's not surprising because it has to do how we define how temperature or how we chose our processes, and that the bath was exactly at the Hawking temperature that we find it back, because the temperature here can also be seen as the temperature of the bath is during a reversible process, which is exactly the Hawking temperature. The same thing, which is maybe a bit weirder, we can also calculate an angular momentum temperature. So kind of the thermal distribution or the temperature of the angular momentum, which comes out if you look at thermodynamics, where not only energy is conserved, but angular momentum. And there you find also a result, which is also the result you would predict if you just look at the distribution in Hawking radiation. And because charge is also conserved, you can do the same thing again, where you also get a result where this phi can be physically interpreted as the electrostatic potential. None of these exact expressions, but long, you can find it in the lecture notes. And this is also what you would expect to find from Hawking radiation. So also the temperature this entropy predicts is the same, or is the one you would also predict from Hawking radiation. So now we come to this process, which will also be discussed in the exercises, and that Renato already started talking about in the last lecture. And this is this Gadow process, which can actually seemingly violate the second law as it has been stated in this framework and also in other statements. So what do we do? So we have this black hole, and we have up there again a box which we lower into the black hole. And this box has some mass mu, and we might have filled this box. So we idealize this box a bit, so it has no mass. And this box is filled with energy from a reservoir R at some temperature Tr. So what we do is we fill this box, we lower the box to the black hole until the event horizon, drop it, and then drop the contents, pull it up again, and fill it up again with radiation. So what has happened during this process? The work done on the black hole during this process is just minus gained the work minus mu while lowering the box. Then the black hole state, the initial state of the black hole is equal to the final state of the black hole is equal to just its mass, while the reservoir, so write down the system, while the reservoir has initially some energy U0, so I can the state of the reservoir, as by definition of it, is just given by its internal energy, and the final state, because I took out some radiation of it, is U0 minus mu. So then we have violated, or this process violates the second law, because we lowered a box towards the horizon with mass mu. We gained this mass back as work. So we extracted work from the black hole while nothing else changed except the reservoir. So the process is cyclic on the black hole, and the reservoir changed a bit, but that can happen during the in our statement of the second law. So we have found a process that violates it. So let's first just simply look at how, if we maybe slightly change the state of the black hole, but how it has to change that we don't only violate the second law, but also that we don't violate the second law either directly or indirectly. So we assume that the black hole now, or we slightly change the black hole, so maybe the process. So we consider a process P prime, where the black hole final state is now then given by some m plus something proportional to mu. And in this case, if you just look at how, if energy is still conserved, the work of this process prime is then, it's then slightly less efficient. So because some of it went into the black hole. So now we don't directly violate the second law anymore, but we can still maybe violate it indirectly by, for example, violating the Penrose theorem, which is derived from the second law, or the entropy theorem. So let's first consider the entropy theorem. So the initial entropy is just the entropy of, or the initial entropy is the entropy of the black hole, which is, as we know from before, 4 pi m. So now we consider the black hole to be non-rotating, plus the entropy of the box, which has to be smaller then the final entropy, which is the entropy of the new black hole. We lost the box. Slightly rearrange this equation and assume that mu is small, then we can find that there is some bound or some relation this pi has to fulfill. So the S box has to be bigger than this. And we can also estimate the entropy of the box. Just by applying Penrose theorem to just the reservoir, we can figure out that the entropy change of a reservoir, if we just extract energy mu, is just given by the mass, the energy that's extracted over the temperature of the reservoir, divided by formula. So this is just the temperature of the reservoir. It has to be bigger than the temperature of the reservoir. We also find the same equation by actually considering Penrose theorem. So for Penrose theorem, and in this case, we first consider the Diablerets process, which acts on the black hole and the reservoir. And now we consider the process we use, or to reverse it, we just use the process we already found by calculating the entropy. So we can actually, we've already calculated the heat, and the heat during this reverse process, so which acts on the reservoir R2, so this might be reservoir R1, is given by this expression, which you can just calculate from in a similar way as we did during the entropy. And the temperature of this reservoir, the temperature of the final black hole, we're reducing the mass. And in this case, if you apply Penrose theorem, the heat flowing into reservoir R1 divided by the heat over the flowing into reservoir R2 has to be smaller than, or which is equal to this expression for QR2. So the heat flowing into reservoir R1 is just given by minus mu. Because we take out energy mu from the reservoir. And this has to be smaller or equal than the temperature of the reservoir R1 over the temperature of the reservoir R2, which, if you calculate it, is 8 pi the temperature of the reservoir. If you then simplify this entire inequality, you find the same equation if we assume that mu is small. The high 8 pi m has to be bigger than the temperature of the reservoir R1. So this means that we now found, or all the consistency checks we did, if this inequality is fulfilled, we find that the process doesn't violate the second law anymore, either directly or indirectly. So let us now see how this process, or how this would be implemented, or how this can be seen. So there are, or we consider two kinds of ideas. The first was considered by Bekenstein. In this famous paper in 73, where he says, okay, this box has to have some gas at some temperature in it, so it has to have a minimal size. And he considers it to be spherical, so it has a radius B. And if you have a minimal size, I can no longer bring it directly to the event horizon. I have to stay a bit away from it. So I have to stay at least distance B away from it, otherwise half my box is already in it and I can't open it anymore. And then you can calculate how you're no longer as efficient. So you again have this high happening, and your mass of your black hole increases by a bit. And if you do this, you find that this phi mu is given by mu b over 4 times the mass of the black hole you're throwing it in. So now we can use this equality. You find if you consider, okay, this box has to have some finite radius, and plug it into the inequalities we found by just considering we want this process not to violate the second law. And what you find is actually quite remarkable, is that you find that 2 pi b has to be bigger than the entropy of the box over the mass of the box, which we've also found to be bigger, 1 over the temperature of the reservoir. And what you see here is that the black hole actually completely fell out. So there's no dependence on the black hole anymore, which means there are some relations between the temperature or the entropy and mass something can have, even if we're not actually considering black holes. Just the existence of black holes and processes like this would imply, if we assume our axioms to be true and these processes to exist, would imply that there is some lower bound on the size and energy certain objects can have. There's also been a second approach to resolve this process, which was presented by Wald and Unruh. The references to these papers also in the lecture notes, and they assume, or they were a bit later, so Hawking actually already had this calculation of, they knew that black holes radiate, and their idea was to use radiation pressure. So their idea was, okay, we can only lower this box so far, so we will lower it and lower it and lower it, and the black hole radiation will push against the box, and the process they calculate is the most efficient if you lower it so far that your strain tension is 0, so the box is buoyant in the radiation. It's buoyant in the radiation, so you have lower or most efficient until buoyant, and then the second law is also not violated. They argue that, so you have outside you have thermal radiation, which maximizes entropy for a fixed volume and energy, and the box is buoyant if the energy in the box is equal to the Hawking radiation energy of the spaces. And so because the entropy that's losses the entropy in the box, so then the entropy cannot increase because the entropy in the box is not maximum, or certainly or lower or equal than the entropy of this thermal radiation. So however, this process, or this idea of trying to violate the second law is by packing too much entropy into things cannot totally be eliminated by this kind of movement. Because you can also make another thought experiment where you have a box that violates this inequality, and then you collapse this object into a black hole, and then you again have the same problem as here, because your black hole will have the black hole entropy, which is just 4 pi m squared, which will be smaller if it violates this inequality than the entropy of the box. So, and the statement of Bekenstein, which is also called the Bekenstein-Cassini bound, because Bekenstein kind of first proposed it, and Cassini has then been able to actually state in quantum field theory rigorously this bound, and also prove it without, for example, what we assume that the second law holds, or that these processes are somehow doable, just on these arguments. So that's, and you will look at this process also in the exercise, but I think you will use it to calculate the black hole temperature.
You finished?
Yes.
You're the first person to finish, not only in time, but before that. Thank you, Ladina. Questions you can ask now for everyone, or you can also meet Ladina in person. Coffee will only arrive in half an hour.
If you still want to, I can still present Bekenstein's original argument to the right entropy, which is a bit more information theoretic, but you can also read this paper.
This is in the notes.
It's in the notes, and this paper is also very accessible, so it's in the reference.
Yeah. That's okay. If there's no left questions, I'll stop the